Hi, my name is Siyuan, and my project is aiming at building a digital twin for the company's manufacturer. And the specific manufacture process in my PhD is the forming process, which is a very important stage in the liquid company's forming, liquid company's modeling. And before the resin injection, it is very important to shape the 2D drive preform into the 3D. And a difficulty here is to eliminate the wrinkles because this material is very sensitive to the double curvature and anything here. If the wrinkle is not removed, there will be a very big reduction in the strength. So eliminating the wrinkle is the target, and it is very expensive to make the physical trials in the real world. So we use the finite element model. But it is very accurate, but traditionally very CPU intensive. And also another problem here is that the material has some variability, which give a lot of uncertainty to predict the process. So our question is how can we optimize this process with as much as the cost without having to run like a sort of simulations of physical trials. So my work involves 3 stages. So the first stage is to build the FE model, which is to model the process very accurately, but we can't have a lot of modeling to run. And the second part is to train a Gaussian process emulator. It is a surrogate model to model this small data set. And the third part is to build, for the real-world validation, to build a forming cell, which can measure the material variability and the wrinkles. So all of this work, the combination of the work, will go into a digital twin. So we'll go to the first part. The FE model I'm using is called Hyperdrape, which is a subroutine that developed in BCI several years ago. It is very accurate, and the main feature of this model is it can isolate the in-plane and out-of-plane behavior. So there is a picture in the bottom to compare the simulation results with experiments. So it is shown that the wrinkle can be perfectly captured, and the fiber orientation can also be captured well. And 2 experiments is required to character the material. The first one is a by-extension test, which is to measure the shear curve. And the second one is the cantilever test to measure the bending stiffness. But it is very CPU intensive. So we're going to build a Gaussian process emulator to model the data that's generated by this FE simulator. So the Gaussian process as a surrogate model or machine learning method, the main advantage comparing with other methods like neural network is that it is very good at modeling the small data set. And also it has a natural ability to quantify the uncertainty and its propagation. So it is very suitable for this kind of problem, which that the data is very expensive. And there is 2 very important algorithms that used in the project. The first one is called sequential design. It is also well known as active learning. So based on this method, I start from a very small data set, and then I iteratively to decide the next position for the point. So this can be the position that can be the most efficient. So after not too much trials, it will can be converged to the optimum. And the second algorithm here is called dimension reduction, and the method is active learning, active subspace. Sorry. So this will help you to model a very high dimensional parameter space, and without using too much data set. And based on all of these virtual things, we're going to do some physical trial to validate the process. So I built a forming cell in the lab, and the main feature is that it has 4 cameras to construct a multi-cameral DSC system. The function of this system is that before the forming trials, we can measure the material variability. It's mainly the macro scale, like the variance of the fiber orientation as the uncertainty. And after the forming trial, we can measure, like use the DSA system to reconstruct the 3D surface and also track the shear strength. So in this way, we can reconstruct the real-world surface and compare that with the simulation under the same scale. So in the bottom picture, there is a comparison between the simulation and the physical trial. So based on all of these virtual things and real-world things, this will lead to a digital twin for the forming process and other manufacture process. And in the future, this will lead to the combination of the FE model, the Gaussian process model, and the real-world monitor system will lead to a zero defect, zero trial, and zero crap manufacture system, and upscale to the industrial applications. Thank you very much.